The objective of this practice was to understand hardenability and how the JOMINY test is a way to measure hardenability of a specimen. The objective was to apply it on a 1018 steel specimen and understand the further applications for this specific hardenability.
In this practice, the equipment and the material that we use and the JOMINY device, so the muffler and the equipment for protection of the muffler, that are the face mask, the gloves, the raised plate. We use the Rockwell hardness tester, and this tester must be with micro anti-displacement device because we must do the proof in different points. The surface grading machine, we use a vernier, a bakery, and welding machine.
For the experimental procedure of this practice, we need a specimen shown in the figure. It's of a height of 100 millimeters and in diameter 25 millimeters. Then we need to determine the temperature of the muffle. For this, the steel need to achieve the austenite phase, and we using the phase diagram with the intercept of the A3 curve, which is 840 Celsius degrees, and with some 55, which give us like 900 degrees. This is the temperature that the muffle needs to be. And then we clean the JOMINY test specimen of grease, rust, and dust, and introduce it in copper sulfate solution for 5 seconds. And then we put the specimen in the muffle for 30 minutes, which is in the temperature of austenitization. And then we open the muffle and hold the specimen and introduce it in the JOMINY device. This needs to be in less than 5 seconds. And we rest the specimen here for 10 minutes and then cool the piece in cold water. Once the specimen is cooled, we remove the copper layer for approximately 0.4 millimeters in deep, and then we measure the Rockwell C hardness for every 16th of an inch in 2 inches, and we graph the JOMINY curve and determine the index of hardenability.
So what we have done in this laboratory practice is to put a sample in a hole to cool down an end with water and the other at room temperature. So the bottom end that is cooled with water create a martensitic phase, and the upper end creates a bainite and pearlite phase. Thus the hardenability is lower by the length and or the distance of the sample. And we have this graph that give us information about the hardenability.
With the distance and the hardness that we obtained from the experiment we did practice, we plot a JOMINY curve that in the vertical axis we have the hardness and the horizontal axis we have the distance. From this plot we can see that the hardness is decreasing very quickly when we have a large distance from the beginning of the specimen. On this slide we can see the indexes of the JOMINY test. Here we have the distance from the first part that was called the Rockwell C hardness, and the index is formed with these two properties. First of all, we put a J, and this number represents the Rockwell C hardness, and this is the distance that we have here. For example, this is a distance of a half of inch that has a hardness of 10.7 Rockwell C.
This graph shows different JOMINY curves for different types of steels, and these last ones show the wants for plain carbon steel for 0.4% carbon and 0.95% carbon. Therefore, our steel 1018, which is 0.18% carbon, will be similar to this curve, and we can see that it starts high and immediately drops down, which is similar to the experimental curve in which we found. In our experimental curve, there were several peaks later on, but these were just due to experimental errors. But in general, the curve shows the tendency we see in this curve.
The ESTM standard for the JOMINY test is a method that covers the procedure for determining the hardenability of a steel.
It covers what we already said in the experimental procedure.
The ASTM defines hardenability as a measure of the depth to which steel will harden when quenched from its austenizing temperature. Therefore, it is basically the ease in which a steel forms martensite. In addition, the severity of temper refers to the cooling rate, and it is how high this cooling rate is. A high cooling rate means it is a severe temper. The real critical diameter refers to the diameter of a bar that has been quenched in an infinite quench medium, and that at the center 50% of the material has become martensite. In contrast, the ideal critical diameter is this same parameter, but in a real quench medium. This diameter depends on the severity of the quench medium, the percentage of carbon, and the grain size. A perfect quench refers to a quench that is immediate. It's when the whole piece, the surface and the inside, cools immediately and the whole phase is transformed at once. In contrast, a correct quench is the actual quench with a real cooling rate, not an infinitely high cooling rate.
For a typical ASTM grain size of 6 for the steel 1018 and 0.9% of manganese, we have the constant for carbon that is 0.17 and the constant for manganese that is 2.4. Thus, the ideal critical diameter is 0.408. Thus, that means that it has poor hardenability, as we already said.
And this table correlates the distance, the JOMINY distance, and the cooling rate. And for example, at a point in 25 millimeters from the JOMINY temper end, which is 1 inch, the cooling rate is 5 Celsius degrees over second.
The hardenability increases with increasing the austenitic grain size because the grain boundary area is reduced. This means that there is the sites for nucleation for perlite and ferrite is reduced in number, and with that the process of this is slowed and the hardenability increases.
The level of hardness depends in part because there are other factors, but depends of the structure, the thin grain size, and the existence of planes that do not permit the displacement. And when the material is fully or is supersaturated, the atoms can move, and for this there are no displacement in the structure. The more hardened structure is the martensite, that is the structure that doesn't permit the displacement, that it happened with a BCC structure transformed to a BCT structure for a temper or quench used in a heat treatment. When the steel has alloy or is alloy, has a very hardenability, and when the content of carbon is high, for example more than 0.3% of carbon, has a better hardenability than the alloy, and the high carbon steels has better hardenability.
In this practice, I learned how the hardenability is affected by the composition of the alloy. Our plain carbon steel had a very low hardenability. However, if it is an important property that an application requires, we would need to search for a different series of steel.
In this practice, I learned the procedure of doing a JOMINY test I learned the way hardenability is measured and expressed, and the way it is plotted.
I learned all about JOMINY test and an important property that is hardenability and how it affects the material. For example, we have to choose wisely in heat treatments to have a uniform cool rate, and if we have to choose a manufacturing process like welding.
In this practice, I can learn about the hardenability of the steel. That is an important characteristic because if we do a heat treatment, the hardenability must be different are the depth of the cooling rate, and it's important because we can have different hardness in different points.
Practice, I learned that it's very important to JOMINY curve. I can see that it's very important to plot this curve because you can see the behavior of hardenability, and also I learned how to obtain the JOMINY index.